our next speaker, I invited her because I've had this experience where I've written some software and put it aside, side project, I put it aside for 6 months, and when I came back to it, it didn't run. Like, it just didn't work. And, digging into it, I realized, like, my whole machine had changed. Stuff had updated, and things were, the APIs were different, or just different enough that it didn't run anymore. And that was only 6 months. We're spending years of our lives building software. And if stuff breaks after 6 months, we're putting years of our lives into this. How can we let this happen? So, I don't want to give her talk away. So please welcome to the stage George Kierstein.
Hello. So my name is George Kierstein, and the work I'm presenting and the talk in general is based on my time at the National Climate Data Center, which is now the National Center for Environmental Information, which is the nation and kind of the world's archive and main research center for climate data. So the talk also gave me a great opportunity, kind of like Bill did, to nerd out about some problems that I'm really fascinated by. And one of which is something I've coined as a generational scale problem, right? What's a generational problem? Well, a generational problem is a subset of these terribly difficult problems in which the time scale and the time course of change is slow enough that we are cognitively blind to them. And we therefore have no kind of intuition in which to ground how we approach these problems. And so they're really tenacious and very difficult to solve. I like to call them dragons all the way down. The other part that I find really fascinating is how the origin of civilization and what it can teach us about the evolution of organizations. So let's get started. Okay, so hibernation. It came out of a project that I was assigned to do, which seemed, to the people who gave it to me, kind of simple, right? So the story is, someone was about to retire. In fact, I have notes for this. Professor Jang Yu-chong started this project in 1995, and a couple of years ago, he was about 80 and he was retired. So he was the main contributor and to one of the biggest and most important climate data models called the Global Surface and Atmospheric Radiant Fluxes model, ISCA, right? So there's a lot of climate data models, but this one is what most of them are built on top of, and it's satellites measuring how dense the cloud cover is, among other things, all over the world. So satellite database, he's been refining this model for since 1995, and he's retiring. The next version was due out, but the satellites haven't been launched yet. And so what do? He has this incredibly large code base that basically only he knows, grad students, other contributors, sure, but it was his baby, and he needed to retire and put it down. So this is a pretty common, sort of scenario in, I think, generational scale problems, right? Some of the code bases in the building for, climate data research go back over 20 years, easy. So they thought, let's figure out a way, and it's your job, to figure out a way to put this away so it'll run again later. Great. And on some sense, I thought, well, how hard could it be? Knowing that the short answer is, of course, it's not really possible. I mean, that example is great. Can we really expect that at this time? No. But some of the things that were really interesting that I thought I could base some kind of solution on was some of the constraints, right? So the constraint one is not the Wilbur time scales. We're not talking about 5,000 years. Maybe a couple of years, maybe a decade, if we're really lucky, decades, right? Or unlucky, as the case may be. Some of the things that pose real problems here that the original author is not available. And when someone is set to bring this back up to life, there is no domain expert to help them. So they're pretty much on their own. The software is ostensibly a black box. And, for our organization, it was also no VMs or containers. That was, at the time, a technological constraint. But I kind of think, if you step back and look at the problem, that VMs and containers really are kicking the can down the road, right? and in some way hiding complexity from the person reviving this that is worse, not better. And that's a debate we can have later. So given all of that, I came up with essentially a protocol instead of any sort of software. It was a simple sort of set of directives about how to package things up and what to include in this package that I thought would give the person who was reviving this the best chance they had, right? So it's a human scale solution. There was no attempt to try to think of what good automation can I do that will solve this problem, because in a very real way, again, it drags all the way down. People have never really tried to do this before. So the chances that an organization that is underfunded and not technically as sophisticated as others are going to really understand any kind of automated solution that would have to be maintained too seem not possible. So the best we can do in this type of problem, I think, is come up with a human-based solution. So the human-based solution basically leveraged, and I'm not actually going to tell you the details of this because I think in reality they're not that interesting, right? And on the basis of my talk, what I'm going to try to argue here is that it's not for any particular solution, really. It's whether we can reason about this problem better than we have, which is to date really not at all. So comprehensibility seemed like a fundamental principle, and I kind of took the approach of, my future self, right? Everybody kind of, pop culture, think of your future self. If you, and now this has happened to me in practice, and then probably to many of you, right? Years later, luckily for me, I was at a company a really long time. So years later, I had to fix these bugs and kind of look at very old code. And I got really upset about the design decisions that were made and the styling until it sunk in that I wrote all this code. I forgot, right? I had no idea. I looked at it fresh, and I was mad until I knew it was me, right? And so the future self kind of model is not a bad one in this case. So comprehensibility is really important. Can you even comprehend the basic structure of the layout of this thing that you're trying to get to know and get to work again? Simplicity in that sense is essential for comprehensibility. How else could you try to figure it out? Well, if it's super complicated all the way down, this is going to take a lot of time, and you might not be able to do it. And one thing that's been referenced in a lot of talks and kind of general theme, I think, is context is important. Because context really matters, so we force people to front load as much information as possible, go through great lengths of documentation and architectural decisions that had been made that they never wrote down, in order to provide as much context as we could for whomever had to get this to run again. So that kind of was the sort of main thrust of how I approached this problem, which kind of led me to feel pretty good about myself. I actually won an award for my protocol, which was kind of ridiculous, because essentially it was like, just please, have good hygiene, do things sanely, be sympathetic to whoever comes next, and yet that was still a novel idea at the time, and in that organization. And this actually brings us to the bulk of the talk, which is, well, that worked out well for them. We got ISKIP put down, and we, did the test to make sure we could revive it at least once with someone other than me in production, and that went as well as could be expected, which took a month, by the way, which tells you something about the time scale, even in a very controlled circumstance, when we literally had the guy who knew how to get it to run, sit down with me, kind of do things to the minimum we needed to kind of revive his code and put it away, and it still took somebody a month. Organization, like, DevOps took weeks to respond to us. Dependencies were missing that we didn't even notice at first with the way they set up their deployment machine versus sort of our development environments, right? So that's pretty sobering already, and kind of speaks to the kind of level of complexity and how bad this, or how difficult this problem space really is. So of course my intuition when they said, hey, well now that we've got this fancy thing, we're under budget and we don't know where to put all our data, and we have like 70 new data sets coming in, so why don't we, brilliant idea here, just brainstorming, why don't we just replace all of our actual data that we take so much time to have provenance for in the Dr. Sussman kind of provenance way with, the program and its inputs. Save us so much time, so much space, would be great. And of course, horrifyingly, no, right? No was the sort of response, but trying to articulate no with something more reasoned than like, you can't get me to do it, like no, kind of thing. I'm not going to help you, and hand wave no, kind of led to a lot of the rest of the talk, which I'll get to next. So, can we do better than just saying no? And let's give it a shot. And as we do so, I'm going to leverage some points of inspiration from sort of the generational problem perspective and historical perspective of how civilizations have been formed and how they organize themselves to solve big problems. So let's do what everybody does, right? Let's go back to the, Newton age. When we have an awful problem we don't know anything about, let's just define it. So we're going to say survivability is S. You with me? Okay, so, well, let's try to constrain the problem space a little bit. Because survivability of any kind of system, and software systems in a very real sense now, can be conceived of as an ecosystem that sort of lives and breathes and thrives and dies. There's a lot more to it than sort of we could really lay out and tackle all at once. But there is some part of it that we might be able to come up with a better model to actually reason about with. When I call that resilience, right? So what do I mean by resilience? In the sense that software is flexible and adaptable, resilience is this property in which it's sort of resistant to change or can cope with change well. So resilience in my mind and intuitionally is kind of inversely related to how fragile something is, right? And that's almost definitional, I want to guess, from English language. So let's call resilience the inverse of fragility, right? So now we've got a model, we're on our way. So I'm reminded of Tim Gunn, who says, steal from the best and make it your own. So industrial engineering, for example, is a field in which they've really looked at this problem of how you go about sort of looking at how things break systematically in some kind of production sort of system. Now, of course, emotionally, I hate this, and I'm like, well, I'm not an industrial engineer. I'm a special person who, just like all of you, is like above average, right? I'm an above average programmer like everybody else. And so I didn't like this very much emotionally, but let's give it a shot because they've done a really good job. So they kind of have, when you pick up an early text on industrial engineering, they talk about defect rates, right? They have nice models, and they say, okay, we can model a defect in a system like so, right? So, and kind of like Dr. Sussman mentioned, as a skew, I define it as drift, right? So how fast and far does the system, the parts of the system loosely that cause things to break in this respect drift? And in our problem space for this tiny problem where we put code away and it's well defined, and we bring it back up and we just expect it to work, we avoid a lot of the other kinds of problems like adding things or what happens when we send new inputs to it. Since that's not our concern at this point, this is really drift of dependencies that break. Like what really causes these systems to fall down? Well, in practice, it was the dependencies. The algorithm or the nature of the thing itself, that didn't change between the time we put it away and when we're pulling it back up again. So let's just call them D. That's drift, and it's about dependency drift. And maybe, if we're lucky, we could figure out eventually a statistical model. Now, of course, that seems ambitious and dubious at best, right? Because who knows if any kind of simple statistical model like a Poisson distribution, which is kind of the baby steps of industrial engineering textbooks, has any application to what we're talking about. In fact, maybe a stochastic sort of statistical approach might be a better fit, and possibly even acknowledging that this is really a complex system and we have to start talking about the phase spaces of its stability and all the rest of that as some interesting books on kind of the relationship between stability and complex systems and computability. So who knows, right? But given that on some level, like my Game of Thrones book club's house motto, we do not know, we might as well start with something simple that we can reason about and try to put our intuition into a form that we can, make more useful and argue about later. So let's call this resilience now kind of have a proportional relationship to the inverse of the drift of our dependencies, which for our problem is more or less, kind of describing that dependencies break, and the chances of that system being resilient is inversely proportional to how bad and fast they break. Well, let's start to put some nuance to it, which is the magnitude, right? We kind of don't want just the number of the potential for it breaking. We want to characterize also how bad this is going to get. So the magnitude of impact here is what we define as that. And then here's my papers we love moment. Can we put a bound to that magnitude, right? Well, there's this great sort of online paper called The Mathematical Limits to Software Estimation, which I love. He had a background in CMMI, so did I, interestingly. And I'm not going to get into what that is other than it is kind of the sort of 80s level first wave attempt to put any kind of systematic reasoning around and modeling for software estimation. We kind of would put it aside except in places like the government, and we've kind of gone with the hand-wavy estimation by analogy. But this paper uses Kolmogorov complexity to try to analyze whether or not that's even sane or possible. And the upshot really here that I want to get at is that ostensibly, no, it's not. If you're doing an estimate, your estimate can be off by as much as rewriting the whole thing, which is a sobering thought. And in a lot of ways, kind of harkens back to, I love referencing people because everyone's been so great at presenting things that are super interesting. Kim Creighton, talking about the myths of programming and how we should change our culture to, sort of be science-based about it. One of the myths that I had a whole rant that I took out of this talk is around the 10-time programmer and estimations, kind of our cultural bias towards believing we can, kind of perpetuating some of these myths. But basically, the upshot of that is we don't believe these estimates. And that should be really a sobering kind of criticism of this 10-time programmer, because I pat bet 2 times 3? Most people do. And as a manager, I took other people's estimates and did the same thing, right? So now we typically always kind of just by nature pat out against this, order of magnitude that people are supposed to have. So, that seems pretty sobering and bad, but that does give us some kind of bound, right? Well, in our problem, the worst case for us is we have to completely replace the dependency. So that theoretically is a task we can understand that takes a certain amount of time. So let's run with that. Let's just say we have a linearly independent set of dependencies, which of course is dubious, but again, simplicity and who knows. So now we have this nice series here that will sum all the dependencies and give us some kind of number. So we've got a metric, we've got a model. And I'm going to segue now, because where's that D going to come from? Is that even accurate? Who knows? How are we going to find out? And so I'm going to start to talk from the history of organization perspective, kind of jump forward to sort of one way in which early science went about solving a generational scale problem that in weird ways bears a lot of resemblance to this problem space. So here is the Great Pyramid of Giza, built approximately 3rd millennium BC, but nobody really knows. The interesting thing here is that, that obviously took an enormous amount of time and effort. And this is the vulture stone. I can't pronounce that, so I'm not going to try. And it basically is Paleolithic or Neolithic. It is an amazing piece of art, but it is also depicting what used to be a controversial piece of art, because people thought, the crazy people posited that it was like, okay, this is depicting when comets change the weather, right? They slammed in around that time, 10,000 BC. They brought about this certain period of history, and that caused this climate change problem, caused a big shift in human behavior, and is the origins of urbanization and agriculture, right? Well, nobody believed him until very recently. Some researchers at the University of Edinburgh, in reading glasses, Klaus Schmidt, basically used the model to back calculate where the stars would be, and that was right. Their symbolic depiction of that is really literally down to 109950. They could back calculate exactly when the comets came, They were right. And that really is an amazing depiction that is a historical event with a lot of accuracy for astronomy at the time. And it also, apparently also, they also managed to calculate long-term changes in the Earth's rotational axis from those comet impacts, and they put them on these stone things from their early writing, right? So astronomy and our kind of monument building is really old, and our attempts to reason and put things down go back quite a long ways. And basically every monument building culture were amazing astronomers, right? So this, basically all of them were really amazing astronomers, and they had sophisticated methods to try to build these massive monuments. The city of workers here from the Great Pyramid of Giza, unlike our previous assessment, which is that Charleston Heston and slaves built the pyramids, in fact, they've been able to determine that it was about 10,000 very skilled workers that lived right next to the pyramids, and that in a very real way, they looked at this kind of like the Amish barn raising thing. So they had their entire civilization built around and kind of geared up to build these great pyramids. And so do these monument builders. These are the Moai on Easter Island. They were the monument builders that basically built themselves into existence. That is their kind of story, right? They geared their whole civilization up to build these things, and in doing so, they eradicated all the plants and the trees, and they went extinct. And this wasn't that long ago. So in one way, I argue that this is a pattern for how humans organize solving problems. And we're doing it again on a much grander scale, right? This is the Foxconn factory in Shenzhen. So what are some of the takeaways here? Well, in a sense that I think can be meaningful for us and useful for us, that a civilization is defined by these monuments. We build monuments, and we need to be really careful, as Dr. Sussman pointed out, about what monuments we build and how we build them. Because at the end of the day, they kind of define us in a lot of ways, but on all levels of civilization, right? Every single person in there kind of has a cultural sort of attitude that brings them to work. And, these monuments get built, and here we are today. So another thing that's really fascinating is basically everything I showed you previously. No one really understands how they pulled this off. I mean, just let it sink in. The Great Pyramid of Giza is an immense engineering marvel with precision that we can't really easily replicate unless we're highly motivated, right? So, and no one has any idea because no written record of their building techniques are left. Just like the papyrus, no one knows how this was done. And in a lot of ways, this inspires people, I think, to look to aliens, right? And I think that is a huge mistake, and I have a little Facebook group chat called Pyramidiots, where a friend of mine really loves the Sirius 9 alien sort of thing, but I really argue with him and can't go there because really I think we should never underestimate kind of the human nature of how badly we are inspired as nerds to solve these problems. And that, I think, can serve us in cases as inspiration and a warning to be able to tackle problems that we have, right? This is BG from earlier this week or yesterday, and he said this great quote, "At scale, all problems become people problems." Well, I think somebody and I were talking about it later. All of our problems are people problems all the way down, and I think we have a historical basis and frame of reference to understand that, and that gives us a lot of grounding and a historical reason to take cultural criticism seriously and to do the work to change it when we understand from a principled way that it's wrong and it's building something we don't want. So let's get away from the long past and doom and gloom and talk about something more modern, which is another type of generational problem, which is a global closed system, much like software at this point, discounting aliens. It pervasively impacts all aspects of human life and civilization, and that this time scale causes us to sort of reinvent the wheel with certain patterns, and I'm talking about climate change, right? So I want to give you a quick overview, just a quick history list of the history of weather and climate and what happened when, right? The highlights. So in 1824, one of my personal heroes, Joseph Fourier, calculates basically the greenhouse effect, that the world would be basically far colder if it lacked an atmosphere, right? By 1849, the Smithsonian, with the invention of the telegraph, have given out instruments all over the nation to get people to collect and telegraph them weather reports, right? By 1870, we had a National Weather Service. Our government funded this whole effort because everybody really cared about that. Of course, the war happened and all the rest of this to motivate this a little bit more. But by 1834, right here in New Orleans, the first archive and tabulation unit for all this data was founded, right? And by 1957, it moved to Asheville and has been there ever since. So that gives us a really interesting time scale for how people have gone about solving this intractable problem. So what's really useful for us? Well, I think that we need to really have a collective recognition of the pervasive impact that this problem has in our life and the way we do work and the way we prioritize within an organization. And data collection was a necessity and a passion because of that. Again, culture is built to build monuments. We build it to improve our lives and mostly to build monuments, because one thing that I didn't show you, I forgot to mention from the vulture statue, is recent research has shown that we basically have, civilization starts and urbanization started not because everybody thought that it would be a good economy of scale argument. That happened the other way around. So we started as monument builders, we started urbanization, we did all these techniques after the fact in order to build better monuments. So here we are building a new monument. Data collection is important. Thomas Jefferson, upper left, he was an avid weather recorder. This is an example from 1907, which is an observation, a little bit more systematic, and that is the sort of other main important takeaway point, right? Systematic collection, and what they knew was relevant is what they did. And that's true for kind of the observations of Copernicus and Galileo, as well as for climate data. So I think this was a pep talk, and that we have it easy. So we already have this huge corpus of data. It's disorganized, it doesn't really have provenance, but we do have a lot of data, and we're starting to talk all the time, and a lot of talks touched on this on the conference, that we are connecting these dots. We have classifiable types of problems that are pervasive, people have seen them before, but we're reinventing them again. And we have the ability, luckily, this time, to have a much more immediate kind of turnaround time and impact on the very problem space we're trying to kind of understand. So that's great. So, promise I'll get back to my little model. What can we do about this? So whatever solution that's effective we come up with really will have to have both I'm as a person, avid, contributor, part of society dimension, and a organizational scale one. So we've got to find a way to, what do we do and how do we motivate people to do it? So we need to start with some simple taxonomy, and it almost doesn't matter what it is. I'm arguing that it just can be as simple to be as useful to create a true historical record that we can then automate, do machine learning against, or whatever kind of technique we want. Find that deep, describe it better. So we can just systematically add a dependency annotation. Is this check-in because of a dependency? That's all we really have to do to start a real historical record. Certainly from the open source argument, that will turn what is now a disorganized corpus that can't be searched. And we have no way to carve out how much of these problems that happened when, or because of this particular issue that we were talking about for the specific resilience problem that I brought up. Okay, so how do we motivate organizations to go along with all of this? Assuming that people in general care enough about their sort of struggles with dependency and recognize the utility that these historical examples have, and that dependencies as a class of problems are worth really paying attention to, and that's about all we know. But that's okay, we can start there and we should. So let's test our model though, because we need a way to communicate all of these ideas to other people. And from that, I kind of am going with the wait, so bad at names, bear with me. Kuhn, the structure of scientific resolutions, right? I think we can just, if we can evaluate this model from the point of view that it has got explanatory power and it's better than our current model, which our current model is being teenagers and not wanting to clean up, honestly. You know, that's the attitude, and that's how people treat sort of problems like dependency management and other kinds of things like that. So maybe we can recharacterize code debt, right? So we can use this model in a real way, given our kind of assessment that we have to replace a dependency. That can be money. How do we characterize code debt? Now we don't really, except somebody says it's bad, right? Bad. And we have to do something about it, but then someone further up looks at the budget and says, no, we can do that next quarter, maybe, right? But if you could characterize how expensive it would be, then that would be a very compelling argument to sort of look over time and say, okay, are we actually driving ourselves out of business by ignoring this problem? Right? We're going to have to pay this eventually. So how much is it actually going to cost? Which is typical, for the types of organizational specializations that, like CTOs, that evaluate risk management as a financial problem. Well, we can give it a shot because in some sense, we've got enough historical record where we can actually calculate this cost. If that, sort of building that library dependency into your project took somebody, they got paid, X hours or M hours, well, then that's an M that's got a legitimate real world kind of value from that point of view. And then, of course, you have domain experts who you ask anyway, like, how long did that take you? And then they say, I don't know. But then they pad it by 10 and they say, oh, a month, right? So even if that's not accurate, at least it helps the management and the organization reason about this problem in a more principled way, I suppose. So I guess our model has some utility, which is great. So I'm not saying this is a great model, but we have to start somewhere. And if nothing else, it should motivate people to think that we can take all of this and actually solve some of these corners of these problems, based kind of like old school, early science sort of way. So what else can we do? Well, I argue that we need to build an archive, but I mean that in that historical way that includes real provenance, right? So we need companies and organizations and actually our entire civilization, ultimately and idealistically, to value this enough to say, we should pay for all of everything. Hire people, train people, let people study this, and more importantly, let's keep track of it all and do it well and with a lot of systematic consideration. One thing that would be really useful, because we need every citizen to participate, and there's a lot of corporate citizens with code that's locked away. Enormous amounts of our code is mostly hidden from us. And that's sort of the biggest criticism of the sort of private versus public open source kind of ecosystem that we're in now, because that data is going to help us solve our problems. And we've got to have a way for them to contribute it to us that is not frightening to them. Motivate them to say, okay, we can strip all of our intellectual property out of this and maybe anonymize names of functions and stuff, so that we can, feel safe about contributing at least this much information. But that's not that hard, and that's a problem we can kind of solve, and we know how to solve, right? So other people, like Zach Tellman, who had a great talk on and was arguing for a simple taxonomy and the power of names, right? Well, I think they're right, and somebody should really start to do that, but it doesn't have to be complicated, and we shouldn't bicker about exactly what, like just calling it a dependency is really good enough to get started until we know how to better refine our ideas about these things. And finally, that code archaeology is probably a subdiscipline that should exist, right? You know, we have an enormous amount of code. And when I first started looking at Poisson distributions, I thought, it just fits data, you know, and kind of started looking at what I could fit, right? None of it made any sense. But a lot of the check-ins and things, like some people don't have public issue tracking, so you don't even know which problems relate to what check-ins. Some people have terrible documentation in their check-ins. We don't necessarily need that much refinement, although it would be very handy. But if we at least could look at a code base and realize there was some problem related to a dependency in an automated way, so I could troll all of GitHub and start to put timelines and, you know, describe life cycles, that would be great. And it would also provide us with a more kind of historically based and data-based argument for how often problems happen and whether or not we should do something about them. So that is my big sort of takeaway. Thank you.
Thank you, George. All right, please volunteers bring questions. So I had some questions about the monuments. You had a few monuments that you were showing. What are some of the lessons we can learn from, say, the building of the Egyptian pyramids? Is this something where we have to become, slaves to our software, to our data?
Well, I think the sort of takeaway is that our tools and how we use them and in order to build these monuments is kind of what we have to work about and what we should reason carefully about how we're doing it. It kind of gives us a more compelling argument to liberate ourselves from pedantic tools. Like, I hate the idea of open, like daily stand-ups. I think there's no real evidence that that's actually an effective way to run a team. I personally vote for organized chaos, and that seems to work for my group of people. And I think there's sufficient evidence actually to back that. So we don't have to become slaves to our tools. Instead, we should re-engineer our culture from the ground up at every level to do a better job at building the monuments. We have done work to analyze as being the one we actually want to have at the end of the day.
Someone asked about VMs and containers. You said you didn't use them. Can you elaborate why?
Well, to start with, it was a pure organizational constraint. I was just not allowed to use them, so it wasn't even a consideration. Even when talking and thinking later about, like, let's just replace all our data with code, I kind of really think that because even now container wars are ongoing, like, should we have VMs? No, containers are better. Which container? I don't know. I hate Docker. Like, who knows what containerization technology is going to look like in 10 years? Or how far is that VM model that you put away? What happens when that breaks, right? I think that just is a type of problem that you just kick the can down the road. And at least if the piece of code you're putting down ostensibly is mainly kind of the main points of breakage are more directly related to the purpose of that code, you have a better chance as someone who has to become a code archaeologist to get it to run again and reason about the system's sort of requirements.
I have another question. I'd love to have other questions too, so please get them up here. So I worked on a system, it was in C++, and I'd never done C++ before. And I worked on it for 2 weeks to try to get it to compile on my machine. And I believe it was like a bootstrapping problem where someone had configured their machine over years and years, and it just worked on theirs. And so their environment was in sync with the software. But then once you just copied everything in a certain directory to my machine, it just didn't work. And of course they hadn't documented everything they did for the machine over those years. Is there any way to recover that?
Well, I think this speaks to the provenance problem, and maybe we need to stop using the word documentation and replace it with provenance. Because in a way, if we can describe exactly where these changes came from and why people are motivated to do them and have any level of systemization, did it systematically on any level, then that becomes a corpus of useful data that harkens back to the turn of the century sort of physicists and let's set term when person does more than one thing
Polyvalent?
maybe polymath. But
Polymath?
polymath, yeah, the more popular term, but polymath scientists of that era, they address these problems first of all by like making up definitions and then collecting data they knew to the best of their knowledge at the time was relevant. But they had to do it systematically, otherwise it was kind of useless. And we're grounding in our data now because it's really hard to even make sense of it.
Right.
So in that sense, the provenance problem is pervasive across how we build software. And it's something we're going to have to change our entire culture from the ground up to make it better.
Whenever I look at those tables, they always seem like, wow, they really knew what data to collect. And why is it that when I think of, logging stuff, I always make it way too complicated instead of like the one or two things that might be useful?
Sure, I'm sort of a willful optimist, I call myself, but I would sort of liken where we are if we're going to kind of compare ourselves to big efforts to solve sort of huge and gnarly problems. In the past, we're sort of right at the beginning of what we're doing. And while we're really sort of rightfully, I think, proud of ourselves for how far and how fast and what amazing monuments we've built, the reality is we still barely know kind of things, Lisps invented in the 50s, so we're not that far along in this process. And I think it's okay to cut ourselves a break and, kind of go with the very primitive, basic things we are starting to identify as problems. Dependencies are these weird class of problems that have all kinds of side effects that we would be better off not dealing with. But we don't understand them at all. We understand them in isolation in our little, corner, but not in any systematic way. Because in some sense, I think this is something to do with how corporations have played this huge role in bringing computing to where it is today. And I'm not saying that with any sort of critical, kind of overtones, but because that's been driven, they're very focused on certain problems, and they don't have to share. Like there isn't this sort of civic-minded, kind of attitude towards monuments we're building, which older cultures have. And even early science, people shared, Thomas Jefferson was recording data because that was a great thing to do. Like, let's contribute to science.
This sounds a lot like Alana's talk about Debian, how it's this old project that people contribute to, and they do all the work of making sure things build, even if...
Totally, I'm glad you brought that up, and I wanted a reference for a talk too. We have these entirely rich data sets already. That is one great example of how we're really far better off than our predecessors sort of might have been in the early days of scientific problems, because we have an amazing amount of data, it's not organized, and we don't know how to make good predictions or reason about what's in there, because we've kind of been ad hoc about the whole thing, driven mostly by understanding the necessity.
So do you see something like, you mentioned ad hoc, are there any ideas, is that a question? Are there any ideas of, like a doctor is required by law to have certain kinds of medical records, keep meticulous records about every patient that they see. Is there hope for that in computing, like something like that?
I would be very careful about kind of taking metaphors for how other disciplines have approached, kind of how to collect data and how they want to look at sort of what record keeping they need to have, because their needs drove them to that place over time.
Right.
And the organizations they've built, which have historical precedents, totally human nature, kind of reflect that, and some of them are bureaucratic needs and litigious needs, right? So I think if we keep it simple and, just kind of, sort of confine ourselves to the simplest version of the thing that we understand, which at this point is just noticing this is a dependency, that we will eventually come to have the right sort of balance of the types of things that are useful. Some of these AI questions that have been brought up, around how to codify ethics and rules and so forth, these are becoming problems we really need to sort of have some reasoning about, and then out of that will come the actual record-keeping requirements.
Right. Are we creating, I think I mentioned this in Will Bird's talk, it seems like our software only runs because we just never shut it down. Like we keep running it, like, and so we have like a class of people whose job it is to keep the machines running. And
Oh, definitely. I mean, you know, we're worse off in a weird way than medieval scribes,
Yeah.
you know, because at least they only had to literally copy something, you know. We're told often, oh, like I want it just like that, but throw in this and paint it pink and draw three perpendicular lines. You know, like, wait, what? That's my favorite YouTube video. Three perpendicular lines.
Okay, I can't read the handwriting on this, but it's about a NASA moon landing. Yes, please.
So the NASA moon landing tapes, the majority of them, or certainly the highest quality ones, were lost because the format was not preserved, and so the tapes themselves physically exist, but nobody can read the format, right?
Mm-hmm.
Something analogous to a Docker container would have been able to preserve the ability to read those tapes. Wouldn't that be a big improvement over not having them?
Oh, don't get me wrong. I have nothing against container technology. I, in some sense, wish I could have used it. And, you know, I really want sort of self-healing code that can fix itself for me and, you know, and to sort of put in place when, you know, instead of these ad hoc, you know, primitive methods that seem to be the only sane thing you can do in the face of all of this, right? So that would be great, you know, and I think we could do better than that even. You know, but I think that we kind of can't just assume that that is the solution to this problem, because history makes it pretty clear that that's not how people approach these problems, and that's not how they end up solving them.
And is it a Docker container or a Docker image just another format you have to make sure to stay up to date on?
As with anything pedagogical, you build one on top of the other. We have an entire stack. We even use that word every day. All right, and it works.
Sure, and that's a certain style of solution that has utility, that we kind of have an intuitive, emotional, like, this is great, look at this monument, my stack's 10 deep, you know, or whatever. But I don't think that that necessarily does us the service of trying to take a step back and look how
What's the alternative? That's my question. What's the alternative?
Well, I think the alternative is to continue forward with the things that work, but try to create a corpus of data that can directly address some of these questions so that we can sort of, from a simple taxonomy, like dependencies, you know, other people who are much better qualified and, you know, kind of better thoughts about this could probably build a beautiful, simple taxonomy that kind of looks at our class of problems and can annotate them properly. And if we all go ahead and do that, you know, and kind of are systematic about it, we could have a chance to reason about why that works so well. And when it falls down, how and why does it, right? I mean, there was an argument, you know, of another talk earlier that was about, well, who needs systems language? Well, you know, we probably do, but that's an intuition that this is a class of problems that could be better reasoned about with a better tool, right? And container technology and stacks have taught us a lot about how to cordon off, you know, these dependencies and these levels of abstraction. And I think that's incredibly useful, and we couldn't be doing what we're doing today without some level of it. But, you know, again, we don't really, I think we need to be a little humble in the face that if one of them, you know, that they don't solve all our problems and we don't understand why. And that we can come up with a better solution, but we need better data. We need to take that sort of other intuition that they don't always work more seriously in a systematic, kind of cultural way. And, you know, actually get people who are motivated to deconstruct why and how and compare them to other classes of problems. And I think when we do that, and we don't look at each problem like this in isolation, you know, we can start comparing them to the similar classes of problems. You know, do containers have the same problems as VMs? That's an interesting question. I don't think anybody's, you know, like, I'm not an expert in this, so, you know, but I think that's an interesting question that, you know, how could we have thought about that? We just came up with this stuff 10 years ago, right? You know, we don't have all these answers, and that's okay, because I think we're starting to figure it out, but we need to compare notes, and we need to do that systematically, and that's how we'll come up with these solutions.
Any other questions? Yes.
So in terms of just like day-to-day first steps about trying to go about conscientiously writing a program and beginning to archive and annotate, what's your advice on that? How would that look from assuming that what you are writing will break in 6 months and reasoning about,
Right. Well,
or predicting why it might?
Predicting why it doesn't is kind of the holy grail of
Right.
what we're doing with the data collection, right? But I think the historical record and kind of being conscientious about the provenance of these types of problems you personally are encountering in your code base goes a long way to let you build tools that can help you reason about what happened and why it didn't happen last year, or is it really, kind of this sort of type of library that's to blame. Maybe it's the way we've built our API, but from that you have to, kind of do simple things. Like if you really have constant dependency problems, you should, every check-in that's related to it, do the simple thing and put dependency in, or whatever it is, but you should be systematic about it and, kind of treat it with a certain level of enthusiasm that, eventually this will actually help you search through your code base and your sort of history and be able to start to better reason about the problem space that you're encountering.
So there's a idea of the change log, which kind of has a standardized format and like practices about adding stuff every time you do a release. Are you thinking something like that, or something?
No, I'm being really literal when I say systematically add some dependency add-in to all relevant checklists. If you add a check-in comment, and if it's related at all conceptually to you from your problem space, it should have a dependency, kind of in there, in that comment somewhere.
Okay.
That's the simplest thing we can do, but at that point then we have a timestamp, and we have a lot more information about what changed when, and finally we know definitively, without kind of trying to look at every check-in or remember what we did, that is due to some check-in, like dependency problem. And I think other classes of problems, given a simple taxonomy, you could start your own, can help you carve up these problem domains, and from there you can start to reason about whether or not they really, like this part is what you suspected was going wrong and suspected was influencing this actually has happened. Because right now we just sort of have our intuitions and we roll with them based on our experience, but the truth is those are often wrong.
So I have another card from Hunter. How do literate programming approaches come in?
I love the idea of literate programming, but it's been a really long time since I looked at it, and I don't know. I haven't really thought about that, but that is kind of speaking to we need to rethink what we mean by documentation, right? And I think Kenneth was right about that, and again, here we are, he was older, and I didn't read his books anyway, because I'm young. And I didn't have that right background, and I heard about it. That sounds great. Let's do that. But we do need to rethink documentation, and we need to rethink how we look at what we want to record and how we want to do it. And sure, maybe we can rethink how we program altogether. Because again, the tools that we use to build the monuments are sort of kind of symbiotic and they define us.
But in that sense, literate programming, taken as a practice, and I've never been super successful at it, is not just documentation, it's how we approach the actual construction of the software and the organization of the software.
That's great. I don't really know anything about it, but at the end of the day, that's more sort of evidence that code archaeology as a subdiscipline should be treated like a legitimate thing, and maybe people should start doing that. And then we can get value from it and can justify, the changes that people advocate and the problems, the solutions to certain parts of the problem domain that people are really excited about.
Yes.
All that historical stuff, people were able to kind of date with the stars, like they saw these events, and so now we can kind of guesstimate better when things happen. Is there any kind of log we could add in computering that would provide, okay, I can guess that the dependencies happening between this and this, or these things should work together?
That's a great question. I don't know. I mean, I think that's what we're looking for when, historians try to analyze our own sort of computing history, and, people try to put together talks about how to systematically think about sort of systems versus processes versus these other things. And, yeah, it would be wonderful to take something that, like, all of the dependency management stuff that Elena is working on and tie it into an actual narrative that it's got descriptive power to say, oh yeah, this class of libraries suck, and we should really stop trying to do it this way.
Okay. Well, I think we're going to end it there. Thank you so much.